In this video, we're going to do a brief overview of Poisson distributions. So, a Poisson distribution can estimate the number of events in a large population over a unit of time. So examples are the number of cars purchased at a large dealership in a week, the number of heart attacks on a particular day, the number of typos in the first draft of a book, and the number of marriages in Delaware on a particular day. The Poisson distribution describes the number of such events for a fixed population or number of objects. Here maybe the number of objects is like words per page or something like that, if the events are independent from one another. The Poisson distribution can be used for a unit of time, such as an hour or a week, but could also be thought of as space as well, like the number of pages in a book or something like that. The rate for a Poisson distribution is the average number of occurrences in a mostly fixed population per unit of time. So for example, according to the NYPD, there are an average of 0.46 car accidents per minute in New York City. So here the time unit is 1 minute, and the historical rate is lambda equals 0.46. So we usually use lambda. In this case, lambda is 0.46, is the historical rate. We describe the probability of observing k events in a single unit of time using the Poisson distribution. So here is the formula for the Poisson distribution. Suppose we are watching for events and the number of observed events follows a Poisson distribution with rate lambda. Then the probability that we observe exactly k events over this unit of time is lambda to the k times e to the negative lambda divided by k factorial. So that is our formula. Let's apply it to this particular situation of car accidents per minute in New York City. So let's find the probability of 3 accidents in NYC in a given minute. And so we would use our Poisson distribution above. The probability that x is equal to 3 would be equal to lambda to the k times e to the negative lambda divided by k factorial. In our case, lambda is 0.46, so 0.46 to the k. K is 3. That's the number of events we're interested in, so that's 3, times e to the negative lambda, the negative 0.46, divided by k factorial, divided by 3 factorial. And so that's 0.46 to the third times e to the negative 0.46 divided by 3 times 2 times 1. That's 6 is what 3 factorial is. If you throw that into a calculator or something, you'll get 0.0124. So the probability of exactly 3 accidents in a given minute in New York City, according to this, is 0.0124, or about 1%. We can use the Poisson distribution to model the random variable x equals the number of events in a unit of time when the population is large and the events occur independently of one another. There is a more precise definition of this population is large idea, but we're just doing a brief overview of the Poisson distribution in this course. If you take a more upper level course in probability, this would be discussed. And in terms of independent, there might be situations where the idea of independence is not perfect. I mean, in fact, the example we just did of car accidents isn't really. So a lot of car accidents involve more than one car, and so that's sort of breaking the idea of independence. But if there's kind of relative independence, like there might be a car accident over there and over there and over there, if these events are relatively independent from one another, a Poisson distribution is still useful to model it, and in fact, Poisson distributions are in general used to model accidents. Another thing to think about sort of improving if you're talking about this model would be, in our example that we just did, there are probably more accidents like at 5 p.m. during rush hour than there are at 2 in the morning potentially. So if you have more information, you could also model this a little bit better. If we had like the average number of accidents at 5 o'clock on a Tuesday, we could better model that for a particular time period. All right, let's take a look at another example. Suppose that in North Adams, an average of 2.4 homes are sold per week during the summer months. Find the probability that in the first week of July, 1, exactly 2 homes are sold, and 2, at least 3 homes are sold. So try that out using the formula above, and we'll talk about it in just a moment. And that formula was probability that x equals k is lambda to the k times e to the negative lambda divided by k factorial. So that's our Poisson distribution for k events where the rate is lambda. Okay, so our 2.4 homes sold per week, that's our lambda is 2.4, and we want to find the probability that exactly 2 homes are sold. So we're looking for the probability that x is equal to 2, and so that's going to be lambda 2.4 to the second power times e to the negative lambda, e to the negative 2.4, divided by 2 factorial. So that's just 2.4 squared times e to the negative 2.4 divided by 2. That's 0.2613 is that probability. Next, we want to find the probability that x is greater than or equal to 3. So, there you could say probability for x equals 3 plus probability for x equals 4, 4 plus probability for x equals 5 plus for a very long time until you got to essentially 0. But of course, it's a lot easier to do the complement. So we could do 1 minus the probability that x is equal to 2, the probability that x is less than or equal to 2 is the complement of x being greater than or equal to 3, because this is a discrete situation. It can be 2 or 3, but nothing in between. What is that equal to? Well, let's first find the probability that x is less than or equal to 2. We've already found the probability that x equals 2. Let's find the probability that x is equal to 1. That would be 2.4 to the first power times e to the negative 2.4 divided by 1 factorial, which is just 1. So that calculates out to 0.2177. And the probability that x is equal to 0 is 2.4 to the 0th power times e to the negative 2.4 divided by 0 factorial. Remember that 0 factorial is equal to 1. And so 2.4 to the 0th power, anything to the 0 is also equal to 1. So this is simply e to the negative 2.4, and that calculates out to be 0.0907. And so then the probability that x is less than or equal to 2 then is the sum of the 3 values we have. The probability that x is 2 is 0.2613, plus the probability that x is 1 is 0.2177, plus the probability that x is 0 is 0.0907, and so that calculates to 0.5697. And so finally, we can find the complement. The event that we're actually interested in is the complement of what we've just found below. So that's 1 minus 0.5697, and that gives us 0.403. Sorry, 0.4303. A Poisson random variable has a particularly nice mean and standard deviation. So the mean of a Poisson random variable is just lambda. That makes a lot of sense because it's the historical average, so it would make sense that it is the current average number of events as well. And the standard deviation is given by the square root of lambda. So let's do an example. Suppose that on Thursdays there are an average of 53 customers at a particular diner. What is the probability of exactly 61 customers coming in on a particular Thursday? And is exactly 61 customers on a Thursday unusual? So think about each of those and we'll talk about them in a moment. All right, so what is the probability of exactly 61 customers coming in on a particular Thursday? The probability that X is 61 is lambda to the kth power, so 53 to the 61st power, times e to the negative lambda, negative 53, divided by 61 factorial. And so if you have some kind of computational device with factorial in it, then you can calculate that to be 0.0287 is the probability of that event. So now, is that event unusual? Okay, so this particular event happens less than 5% of the time. 0.0287 is less than 0.05. But is this unusual? Remember that when we think about unusual events, what we mean is it like unusually large, not just for that particular event, but is a value that extreme or more extreme unusual? So we'd be looking at, to say if this is unusual, we'd really be looking at the probability that X is greater than or equal to 61 and say, okay, does that happen less than 5% of the time? We could, again, start to calculate that, look at the probability that X is 62 plus 63 plus 64 plus 65, and eventually those will trail off. And we could sort of see, does that hit at least 5%? And that would tell us, no, it's not unusual. Another way to think about it is to think about the mean and the standard deviation. So we know that for this distribution, which is in fact discrete, it's just very small little pieces. So we're going to sort of draw it as continuous, even though it's technically discrete. We know that the mean is lambda. The mean is 53 customers. That is our lambda. And we know that the standard deviation is the square root of lambda. So the standard deviation is the square root of 53, and that is 7.28 approximately. So this 61 customers falls just outside of one standard deviation of the mean. So 60 would be one standard deviation of the mean from the mean. That would be the mean plus one standard deviation, and 60.28, and 67.56 would be the mean plus two standard deviations. So the Poisson distribution isn't exactly a normal distribution, but it's fairly symmetric. It's going to be fairly bell-shaped as well. And so we can apply a similar logic. We know that for normal distributions, a value is unusual if it's greater than two standard deviations outside the mean. So remember way back when we talked about usual and unusual values, we said a value was unusual if it was more than two standard deviations above the mean or more than two standard deviations below the mean. So if it's more than two standard deviations above or less or more than two standard deviations below, then it is going to be an unusual value. This is just barely one standard deviation above the mean. And in general, we would say that values that are one standard deviation above the mean are not unusual. For normal distributions, about 68% of values fall within that range. But yeah, we would say that is not an unusual value because it's only about one standard deviation above the mean.